What's up guys, and welcome to this tutorial on question 4 of the 2018 supplementary exam. We're going to be going over Newton's law. Okay, so let's get into the question. Two scale pans, each of mass 0.1 kilograms, are attached to a light cable which passes over a smooth pulley. A mass of 0.5 kilograms is placed in one pan and a mass of 0.3 kilograms is placed on the other, which is shown in the diagram. The system is released from rest. Okay, everything else is given in the diagram as we can see. Okay, then we need a definition, Newton's second law, a very long one, so I'm not going to write it out. Okay, but I will say it out loud. Basically, when a net force acts on an object, the object accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the mass of the object. Okay, so basically, once you've defined it, the equation or the governing equation we get is F net is equal to ma. Okay, that's cool stuff. So 4.2. Okay, consider each side separately and use Newton's second law to write an equation for each side. Okay, so we're gonna consider the left side first. So when I mean left side, I'm saying this side. Okay, so I think we should actually start off by, let's draw a free body diagram. Okay, so we can say that there's a tension T, and we can say we have a mass mg, and that takes into account both these masses, the pan as well as the mass placed on top of it. Okay, and yeah, those are basically the two forces that we really have. Okay, so then using Newton's second law, we can say that F net is equal to ma. Our F net, let's take down as being positive for this side. So if we take down as positive, we have mg minus t is equal to m times a. Okay, mg is going to be 0.6 times 9.8 minus t, because we don't know what that is equal to 0.6 times a. Okay, then if we look at the right hand side, let's draw our free body diagram. It's going to look very similar. This time we have again t and we have mg. Okay, on this side we're going to take up as being positive, seeing as if we took in the previous part we took down as being positive, so we said that this side of the scale was moving downwards. That means the movement would look something like this. So this side has to move up for that side to move down. Okay, I'm hoping that's making some sense. Okay, so we're going to take up as positive, so we're going to say up as positive, and F net is equal to ma. F net is going to be t minus m. We're going to take a 0.4 times 9.8 is equal to mass this time is equal to 0.4 times the acceleration. Okay, so those are our two equations. Write an equation for each, and then basically we could multiply these out, but I'm just going to leave it like this for now. Okay, then it says, hence calculate the magnitude of the acceleration of the system and the magnitude of the tension. Okay, so how would we do this? Basically, we need to carry out two operations, okay, because we have two unknowns. We have t, which is an unknown, and we have a, which is an unknown. Okay, so the first way, okay, so let's start off by looking at the right hand side, and we're going to get everything in terms of t. So what question is this? First of all, 4.3. Okay, so we're going to say our first equation is 0.6 times 9.8 minus t is equal to 0.6a. Okay, then this equation in terms of t can be written as t is equal to 0.4a plus 0.4 times 9.8. Okay, and then we substitute t into there. So let's say if this was 1 and this was 2, we put 2 into 1, and we get 0.6 times 9.8 minus, okay, t was 0.4a plus 0.49.8 equals 0.6a. Okay, now this equation only has one unknown a, and we can solve for a, and a is equal to 1.96 meters per second squared. Okay, now that we know a, we can just substitute it in. So we can say, looking at equation 1, we can say that 0.6 times 9.81 or 9.8 minus t is equal to 0.6 times a, which we just calculated as 1.96. Okay, and if we look at this equation, t is the only unknown, so we can solve for t, and t is equal to 4.70 newtons. Okay, and again, if I'm correct, this asks for the magnitude, so we don't care about the direction, and we get ourselves what's that, 5, 6, 7 marks so far. Okay, so let's do question 4.4 here. Okay, so looking at question 4.4, it says draw a free body diagram of the 0.5 kilogram mass while the system is accelerating. The relative forces must be clear. Okay, so question 4.4 of the 0.5, so that's the left hand side, which we've actually kind of done. So by this, the relative sizes of the forces must be clear, just tells us to draw length of arrows accurately, or to represent the scale. Okay, so if a force is bigger, it must be much larger. Okay, so drawing a free body diagram exactly how we had it, we know that this acceleration came out as positive, so the direction we had initially chosen for the left hand side as being down positive is correct. So we know that this thing is actually moving down. Okay, if we had taken this as up as being positive, then we would have gotten a negative acceleration. We would have ended with minus 1.96. So then we would have known that the actual direction would be down. Okay, so it doesn't really matter. The signs will work themselves out. We just need to understand what they actually mean. Okay, so we know it's moving downwards, so the downwards arrow is bigger, and that would be our weight. And the upward arrow I'm going to draw smaller, and that we can say is the tension, or we can even call it the force due to scale. And from this, we can even, if we want to make it clear, we can say that the weight is greater than the force due to the scale. Okay, and that would be your answer. This entire box would be your answer. Okay, then moving to, and we get 3 marks for that, question 4.5. Okay, calculate the force that the scale exerts on the 0.5 kilogram mass. Okay, so we're going to be taking, we're going to use Newton's law again. So F net is equal to ma, and we're going to take, let's say, down as positive. So we have the weight mg minus the force F that the pan exerts is equal to the mass times the acceleration. Okay, so the mass in this case is going to be the 0.5 kilograms. So 0.5 times 9.8 minus F of the pan is equal to 0.5 times 1.96. Okay, F pan is the only unknown, so the force pan is equal to 3.92 newtons. Okay, cool stuff. State Newton's third law. Okay, again, it's a definition, so I'm just going to read it out basically. Okay, so basically Newton's third law says that when object A exerts a force on object B, then object B simultaneously exerts an oppositely directed force of equal magnitude on object A. Okay, yeah, that's just a definition. And then 4.7, let's give myself a little bit of space, or a lot of space. Okay, question 4.7, describe the force that is the Newton's third law pair to the force that the scale exerts on the 0.5 kilogram mass. Okay, so basically, what is the action-reaction pair? Okay, so we just need to rearrange the order of this part of the question, basically. Okay, so they've given us the force that the scale exerts on the 0.5 kilogram mass. So the reaction to that, let's do that here actually, is going to be the force, the force that the, changing the order, 0.5 kilogram mass on the pan or scale pan. Okay, so all we did was reverse the order. So scale pan exerts on the 0.5 kilogram mass, change to 0.5 kilogram mass that exerts a force on the scale pan. Okay, and yeah, so that question is done as well. Okay, so if I am correct, we've done most of this paper. I think there's just a couple more. There we go. These last two questions, and then we're done. But yeah, so that's it for this video. I hope you guys found it useful, and thanks for watching. Cheers, guys.